Okay, so here we're going to take a look at proving some binomial identities using uh, a combinatorial proof as opposed to an algebraic one. So our first one is we'll start with Pascal's identity. Okay, so we want to prove that n choose k is equal to n minus 1, k minus 1, plus n minus 1 choose k. All right. So the idea here is you want to come up with the counting question. All right. So the question we want to solve here, if we look at here, let's let the n choose k because we're familiar with that. Let that kind of guide our how to formulate our counting question. So what we know about n choose k is that that tells us how many k element subsets are there of the set 1, 2, all the way up to n. Right. So that is the question. Now, our first answer is just, well, that's just n choose k, right? We'll use that directly. All right, and that gives us the solution right away. All right. Now, for the other side of the equation, so number 2, so let's do a combinatorial approach, right? Instead of expanding and combining, let's just kind of think of this using combinatorics, this idea of combinations. So let's focus here on the nth element of the set. All right, so consider whether element n is in the subset. Is in the subset. All right. Now, there are two options, right? Either it's included or it's not included. So here, let's say if n is included. Okay. So if n is included, that means that we have n minus 1 choices left, and also, or excuse me, n minus 1 elements left, and we have k minus 1 choices as well because n is included, right? So now we're looking for a set not of size k, but of k minus 1. So that is the first part, right? So that means that if n is included, then we have out of n minus 1 elements, we choose k minus 1. All right. Now, what about the other n? If n is not included, well, if n is not included, well, I'm still left with n minus 1 because I already know it's not part of it. So that's not part of the ones that I get to choose from. But I also, it's not included, I still need to make those k choices, right? So I need to choose the k elements now from 1, 2, all the way up to n minus 1 out of those. So I still need to make k choices. Okay. Now, if we notice here, thinking of the principle of inclusion, exclusion, these are disjoint, right? So n is either included or it's not included, right? Those are completely separate. There's no overlap in between those. So in order to, now this kind of proves our cases, right? This covers all cases. So n choose k is equivalent to thinking of it, well, either it's in the set and you count it like this, or it's not in the set and you count the set in this manner, and then combine gives you the n choose k. Okay. All right. Now, another way to think of it in terms of the bit string version. So let's say again, we saw just another way to think of this. Here. So I know n choose k gives me the bit strings of weight k. Well, we can think of, well, what if one starts with 0, right? And then we had the rest of these. So then the rest would be here, n minus 1, choose k, right? Because now I have n minus 1 positions, and I still need to put in k once, because it's of weight k. And now let's say it started with 1. Well, I still have those n minus 1 positions to account for, but in this case, I want to distribute k minus 1s across those n minus 1 spaces. And as we see here, right, these are completely disjoint, right? There's no overlap in these bit strings. Okay, let's do one more example here. So here we're going to take a look at what's called the Vandermonde identity. Okay, so the Vandermonde identity states n choose 0 squared plus n choose 1 squared plus all the way up to n choose n squared. That's equal to 2 to the n choose n. Okay, so now let's think why this has to be the case. All right, so we want to think of two separate counting questions. Right now, again, one question and then two ways to answer it. So let's think about our counting question. All right, again, it's useful to kind of look at the simpler part of my identity here. So the 2n choose n. I'm very familiar by now with the choose number, right? And the counting question being asked here is, well, how many n element subsets are there of a set with 2n elements? Okay, well, answer number one, well, that's just directly. All right, that is pretty much our definition of the choose number, directly, right? This tells me if I have 2n elements and I want to choose n, I would use this calculation here to figure that out. Okay, now let's take a look at here, at answer number 2. Okay, so what I want to do is I want to think of, let me split 2n into 2 n size groups. All right. Now, if we think of this in terms of pizza toppings, let one group, right, be, you can think of the first group as meats. And then the second group, as we'll say, veggies. Okay. All right. And then I want to see, well, how can I construct pizzas with n toppings in them? Right. And I have from these groups to choose from. Right. So that means that, well, if I choose k meats, then that means that we are left to choose n minus k veggies. All right. So this is for an n topping pizza. All right, and this is the product principle, right? So if we have n choose k, all right, then to get the total number of choices, it'll be n times n minus k. All right. Well, if, as we saw in the previous one, these are two identical numbers, right? Because again, the way we think of this is you either n choose k is one way to count it, or the other way to count it is n choose the ones that are not in the element in the subset, right? The n minus k elements, how to choose the ones that are out of them. And we proved that in the previous video. So what we have is that this is n choose k squared. Right now, k was arbitrary, so this will hold for k going from 0 to n. So then that proves our identity, right? N 0 squared, n choose 0 squared, and plus n choose 1 squared, etc., all the way up to n choose n is identical to 2n choose n, right? Through our combinatorial approach here. Okay, so as you approach these problems, try to look at the simpler side and try to see, how we can relate a counting problem, right? A basic counting problem, right? And then from there, right, think of, right, what kind of manipulation is being made to show that it is equivalent to the other side of the equation.